Hello, I'm Alex Braylan, and I'm presenting work done with Matt Lease at the University of Texas at Austin on aggregating complex annotations via merging and matching. Sometimes you want to collect labels for tasks, such as for classifications or ratings, and usually these are pretty simple binary multiple choice or numeric labels. One good thing to do is what's called aggregation, which means getting several annotators, whether they're crowd workers or experts, to work on each item you want labeled, and then measure consensus between them to get the benefits of crowd control and wisdom of the crowds. Like, let's say you want to know the capital of Texas, so you ask 3 people. They each give you different answers, so how do you know what's the correct one? Well, one option is you can take a majority vote. The idea is that if more people agree on an answer, there's higher likelihood that that is the correct answer. Despite the fact that this is simple, it often works well in cases where people can agree on the same answer. And in fact, this kind of label aggregation is one of the most studied problems of human computation. There have been hundreds of papers, tons of different models introduced for doing variations of weighted voting that simultaneously estimate parameters like annotator accuracy or item difficulty. And almost all of these models are made to aggregate this kind of simple categorical data. But what about cases like this example here, where you ask annotators to provide a caption for this image? One problem for labeling tasks like this is that the space of possible labels is so big, you're never going to get exactly matching labels. So these kind of consensus models like majority vote aren't really usable. And these kinds of non-categorical complex annotation tasks are pretty widespread. For example, ranked lists, captioning, translations, parse trees, sequence annotations. These are all complex labels and are also very different from each other. For certain specific kinds of complex annotation data, though, there do exist some custom task-specific models. For example, models for text sequences have been developed by Nguyen et al. And for bounding boxes by Branson et al. In 2017. And these can be pretty useful for the specific tasks they are designed for, but they're a bit limited in their applicability to very different tasks. And so the main problem is the lack of generality. You have to come up with a new one of these custom models for every new task type. So in our prior work, we tackled this question of how to aggregate these kinds of labels that are more complex than simple categoricals and do it in a very general way. So our idea was to use a distance function to measure distances between labels. And then you could, for example, choose the most central label as the best one. And we came up with a bit fancier kind of weighted voting model that works off the label distance matrices and considers worker accuracy and item difficulty and such. And the benefit of this distance-based approach is that it takes advantage of the near ubiquity of evaluation functions across various tasks to produce pairwise distances between labels and let you just work with those numbers instead of whatever the original complex data type was for the labels. However, one limitation and criticism of this approach was that it's just selecting the best annotation, which for categorical tasks, which the bulk of prior work has focused on, that was the best you could do. But you're limited by the best annotator label. So if the best annotator label is worse than gold, you're bounded by that. And what you really might want to do is merge a number of annotator labels together to produce a new label that's better and closer to the true gold than any single annotators. The motivation to merge labels like this comes from this classic wisdom of the crowds experiment of people guessing the weight of an ox and their average guess being very close to the true weight due to the law of large numbers, which basically says that the average of more and more random errors goes to 0. And likewise, if we were to average the coordinates of these boxes here, for example, we'd be taking advantage of that law to get a better aggregate box. However, how do we support merging like this in a general way across diverse annotation tasks without having to design a custom merge algorithm for each task of interest? This problem is pretty widespread across various kinds of annotation tasks. Not only are there different modalities of items that you want annotated, such as image items or text items, But there are also different kinds of annotations for each modality. For example, for images, you could be getting bounding box annotations or key point annotations like here on the right. And there's an additional source of complexity for these kinds of annotation tasks that we're looking at. For example, in this image here, there may be any number of penguin objects that you're asking annotators to mark out. Again, this applies to various kinds of annotation tasks. The fact that each item, which again might be an image or a document, for example, each item can contain any number of individual objects for which annotators have to provide bounding boxes or key points or text spans, and multiple of these. So actually, you can use our previous work's multidimensional annotation scaling method on this. It will pick the most central of these multi-object annotations. However, once again, the limitation of this prior approach is that it's just selecting one worker's entire label set per item. Whereas ideally, we would want to combine labels from different annotators rather than select one annotator's entire label set. For example, given this description of the task, highlight all forward-facing penguins in the foreground, we might have one annotator that highlights all forward-facing penguins and one that highlights all penguins in the foreground. But maybe if we could match individual boxes between different annotators and get a mix of each, we could get a much better final aggregate than any individual annotator's label set. So our two research questions are these. How can we merge complex labels, and how can we mix and match labels in multi-object annotations? And importantly, we want to have as generally applicable technique as possible for both of these. The main insights we base our ideas on are the following. First, that complex labels often have a kind of natural decomposition into numerical primitive features. These primitives can be aggregated and recomposed into a new merged complex label. This helps generalize an approach to merging across a wide range of complex annotation types. And second, for multi-object annotations, we can take advantage of these near ubiquitous distance functions to partition the individual labels according to what object in the item they likely pertain to. And this can be accomplished by clustering. Again, this allows for a general approach that can be applied out of the box to different annotation types, varying only the distance function used. For merging labels with numerical features, we start by considering each label being decomposable into fixed length key value pairs. For example, text spans can be defined by a left index and a right index, as shown here. And over here on the right, we show the same thing, but for a bounding box, which we're just decomposing into an upper left XY coordinate and a lower right XY coordinate. And once these labels are decomposed, a merge function such as a rounded mean would give you an aggregate worker value for each of these endpoints. For example, the spans from 1 to 3 and from 2 to 5 are averaged into a merged span from 1 to 4. And this happens likewise with the XY coordinates of the bounding box. And you could do the same approach for the coordinates of the vertices of a key point. So for single object annotations, this merging of numerical points is very straightforward. But what about when you have multi-object annotations, as shown here on the bottom? You don't really want to take the average coordinates of all three of these boxes, right? So for this, we need the next method we propose for partitioning annotations. So recall in multi-object annotations, you have several objects in the image or text item that are being labeled by multiple workers. And the idea is we want to partition the individual labels that correspond to the objects in the item, and then aggregate each of those partitions independently. For example, here on the left, you have multiple key points where each color represents a different annotator. And by partitioning, we could get to this middle image where each color represents a different cluster of key points based on what object we believe they would pertain to. And then we would use the aggregation techniques on each of these colors of labels independently, put those labels back together, and we'd end up on the right here with an aggregate multi-object annotation that has mixed labels from potentially different annotators. Now, how do we actually do the partitioning? Since we don't know what gold objects actually are, we would have to match labels together that we think pertain to the same object. For this, we use a clustering algorithm that takes as an input the distance matrix between the various individual labels. Specifically, the method we use that we test uses agglomerative or hierarchical clustering with the max number of clusters set to the max number of labels from any worker. And we discard any singleton clusters as outliers. So we've discussed how these methods work. Now let's step back and explain how they work together. For both single and multi-object annotations, we have this prior work method here shown in purple, which does all or nothing selection. That is one worker's annotation for each item. In our current work that we are introducing partition and merge. And partition is the clustering approach we just described for multi-object annotations. After they are partitioned, we can either select the best individual label in each partition, or we can get a merged label for each partition. And in the case of single object annotations, we can skip partition altogether and go straight to merge. So for the experiments that we run, we look at 4 data sets, 2 which are simulated and 2 which are real-world data sets. The simulated ones include a new multi-object key points data set generated by taking ground truth key point data from the COCO data set and applying common errors such as rotation, scaling, etc. to get a simulated crowd data set. We also have a simulated ranked list data set from our previous work, which is the only single object data set that we test on. And for real data sets, we have one of multi-object bounding boxes. This is a new data set and one that we share on our repo. And finally, the PICO data set of the multi-object text spans used in Yuan et al. 2017. These are the methods we test. For baselines, the most basic is the expectation from taking only a single worker's annotation per item, which emulates what would happen if you did no aggregation at all. And then we have bespoke models for text spans from Yuan et al. And for bounding boxes from Branson et al. And for rankings, we have this board account method of merging rankings. That's from 1784. The final baseline is our previous work's all or nothing selection approach. And then our methods from this work are partition then merge and partition then select for multi-object labels, and then just merge by itself for single object tasks. So here are the results of our experiments. For multi-object annotations, our partition select approach works better than existing approaches for bounding boxes and key points, and is statistically tied for top spot for text spans. What is not shown here is that this result of partitioning improving results on multi-object annotations is even more consistent across varied experimental configurations and hyperparameters, which you can check out in the paper. For rankings, which is single object, our merge approach is equivalent to the task-specific method board account, which is the one evidence we have of merge significantly outperforming select. In the multi-object tasks, on the other hand, partition then merge does not match the performance of partition then select. The main thing to take away as a practitioner from these results is that this solution that we're providing is very general. It not only matches, but also exceeds task-specific approaches for some very diverse tasks without really needing much extra specification between one task and another. So as you're getting started with a complex annotation task, I would recommend trying this general model first before making the investment to build a custom task-specific model. Let's get into a little more further discussion of these results. So we talked a little bit about merging numerical features. And one question is, what are the different ways that you might represent complex labels, and how does this affect the merging? So for example, we used the corner, the XY coordinates of the corners of the bounding boxes for merging bounding boxes, for representing bounding boxes. But you could also imagine representing them as a 0, 1 binary value for every pixel in the whole image. Now, on a task like image segmentation, that might be fine to represent it that way, which is where you might think of doing it that way. But for bounding boxes, the issue with representing it this way could lead to an end result that's not a bounding box. But this is an interesting question of different representations inducing potentially different aggregation operators. For example, the representation we use for rankings induces this border count merge function, but a different representation would result in the dowel merge. And I don't really know which one is better, but this is an interesting topic to pursue. Another question is the choice of merge function. Which merge functions work best? So some of the error analysis that we did during the development of our methods would lead us to recommend using merge functions that are more robust to outliers. So for example, if you have a one bounding box that's very different from the others, or one label that's very different from the others, something like a mean might be more sensitive to that than a median. Some more further discussion. There's this open question of why select is doing better than merge on multi-object annotations, despite our intuition and some evidence in the single object case that merge is useful. Well, in our paper, we compare against an oracle partition as well, which does the partitioning of the labels according to proximity to the known gold objects. You know, it's cheating to see the known object. But this allows us to do this kind of sensitivity analysis where we see that partition merge performs much more competitively when you're able to do this oracle partition. So my guess is that what's happening is that merging is more sensitive to the quality of the partitioning than select is, and could potentially see greater benefit from improving that partition algorithm. In fact, in general, we did not do very much tweaking of methods and hyperparameters simply because our data sets weren't really big enough to support that much testing. But I could imagine in production, you would want to set out some validation gold data to tweak the logic, especially around the partitioning algorithm, like what clustering methods to use, how to handle outliers, and et cetera. Finally, I'll end on some assumptions that went in to inform our approach's limitations. First of all, we assume the individual labels in a multi-object annotation are a set whose order does not matter. So I would advise, for example, against trying to use this partitioning approach on something like translations, where the word order does matter. As for merging, we assume the existence and validity of merge operators like mean and median for the numerical primitives they decompose to. We also assume this decomposition results in a number of primitives that is the same across individual labels. So for example, you could not use the method we described here to merge polygons of different numbers of vertices. All right, that is all I got. I'd like to thank everybody, and code is available here. Data is available here too. My email is not here, but you could find it very easily and hit me up if you have any questions or need to figure out how to use the code. Yeah, thanks. Bye.